Let's say you're shipwrecked with other people on a desert island and you decide to open a bank. Napoleon brings you 1,000 seashells to put into the bank. You promise to give him 5% compounded monthly for as long as he leaves them in there. 30 years later, he comes back for his investment. How many seashells do you owe him? Well, that would reflect, this here would reflect what's going on there. You have no log tables, no slide rule, no calculator, nothing. But fortunately, there's an abandoned paper and pencil factory with tons of paper and pencils laying around, perfectly preserved, and so you can do all the math you want. So how are you going to figure out what you owe him? This is not some gimmicky fast trick. It took me about 2 hours to do this totally by hand, nothing but paper and pencil, no calculator whatsoever. So first let me stop and talk about other videos leading up to this because this is kind of like a project. This is something that takes some practice to learn. It's for people that are seriously interested in learning how to do something by hand that maybe it bugs you to be totally dependent on the calculator. That's how I am. That's why I kind of made a hobby out of this stuff. But I have some other videos that I have included in the link. And so I suggest watching all of those first. I'm going to use Simpson's rule as the basis for everything. And then you need to learn how to take logs by hand and then take decimal powers by hand and then watch this video. That would be the ideal order. So as I continue, I'm going to assume that you've already watched the other videos and I'm going to concentrate mostly on what's new in this video apart from the other techniques. By the way, I meant description, not link a minute ago. So if you've watched the other videos in the description, then you see that I recommend making your own set of log tables, something like this. And and then if you were really on that island and you happen to do math year after year, well, then you would every single time you calculated a log, you wouldn't throw it away, you would add it to the collection. So these would fill in more and more. You would never throw away, an hour or two of calculation. It would just become part of this. So you'd probably constantly be rewriting so you can put stuff in order. By the way, this is the answer here. This is what Napoleon would be owed. His 1,000 seashells would go up to 4,467. So this is the technology answer. So we're going to do the by hand procedure and see how close we can get. So what I'm going to do for right now is I'm going to just take this part. Uh, we're just going to work it. So I'm going to turn this into a decimal. And when I did that, I got, so I'm not including the $1,000 yet. We don't care about that until we figure out what the multiplier is to go from this to this. So we're only working with this. And this is I pretty much decided to go with 6 decimal places for every time I used a decimal. And so this is just this. And now what are we going to do? Well, we want to turn this into something with e. There's a lot of power in the number e, a lot of things we can do with it. So I'm going to turn this into e to the natural log of 1.04166 to the 360. But that 360, of course, can go over here in front. So I'm just going to go ahead and save space and do that right now. So we have e to the 360 times log of 1.004166. So what we need to do right now is stop and figure out this log. And so I'm not going to spend a ton of time on that. I am going to go ahead and show you exactly what I did, though. Okay, so I did this log. That's what we have. This is the technology answer. This is my by hand answer. And as you can see, it's very good. With tiny values, you don't need, you're going to be very precise with few rectangles. Notice I only did two rectangles here, two sections. And so I used Simpson's rule. This is what I got. And so we're ready for the next step. Again, I'm assuming you watch those other videos so you know what's going on. Okay, so we're up to here now. By the way, I wanted to mention, so notice our delta x is very small. I said in one of the other videos that I recommend delta x not be bigger than 0.25. Really, I think 0.2 is even better. But in this case, it's tiny. So we don't need a lot of rectangles or sections, whatever it is you want to call them. Okay, so that's why we have such precision here. All right, so we went from here. Well, first of all, so just to recap, this is our multiplier times the $1,000. So we went from that to here. Then we went from that to here. I put the log in there. I went up to 6 decimal places. So basically, I chopped it off there. And then here I have multiplied the 360 by that. And now we're up to here. This is what we have to figure out. This is the multiplier. Well, with properties of exponents, we can write this as e to the 1 times e to the all of this stuff. And now really all we need is to figure out this. Once we get that, we're there. And so this, I'm calling x so that we can manipulate things from here on out easily. And so what I'm going to do, I think I'll just use black. So we'll say e to the 0.49652 equals x. And this is what we need to figure out. When we get this, we can multiply it by this. That'll be our multiplier. We multiply that by the $1,000 and we're done. So now it's all come down to this. So what are we going to do? And this is a decimal power. I covered this in one of the other videos. So again, I'm not going to dwell on this a lot. There's not going to be that much longer of a video from this point on. So from here, we're going to, using log properties, we know that this is another way of saying that log of x equals 0.49652. And that other video specifies that now what we have to do, we're looking for an anti-log. So we need to look at the logs in our log tables and see where we are. So let's see, that would put us right in between those two. In fact, those are the two I ended up between with my example on the other one. That was just pure coincidence. So we're between log of 1.6 and log of 1.7. So our x is somewhere in between here. That's how much we have it narrowed down. Okay, so we've got x figured out to be between 1.6 and 1.7. And if you kind of look where this comes in between these two values, it looks like pretty close to halfway. So what I did was I chose to take log of 1.64. And basically, it's a guess and check thing. If I see that I come out with something that, maybe is below this, maybe raise this a little bit, or vice versa. So, but I'm going to go ahead and do this. Okay, I did it and I got this. So as you can see here, I did Simpson's rule. I made my sections. So I did 4 sections. That gave me a delta x of 0.16, which is pretty good. Like I said, I like to be below 0.2 or 0.25. So this is good. And so here I'm doing Simpson's rule. This is what I got. So I'm comparing this to this. and I see it's just below. It's instead of 496, it's 494. So I could have done another one where maybe I took log of 1.64, 1 or 2, and see if I get closer, if maybe this turns into a 6. But I went ahead and just went with this as my value of x. And so from this, we're concluding that x is really close to 1.64, which means we can come up here and we can do, so E, I did 2.7183 times my x, which I'm accepting as 1.64, and that gave me a multiplier of 4.458,012. Well, now we can do the final step. We figured out that our multiplier is this. So we do the original 1,000 seashell investment times the multiplier, and you owe Napoleon 4,458 seashells. You can see how close that answer actually is. So the great news is you can actually do banking with complex math on this desert island. The bad news is after 30 years, you're still stranded on a desert island.